right, this video is going to be about inverses and how we find them for a matrix. So the first thing that we're going to have to do is figure out the determinant, and we want to make sure the determinant is not 0. How do we find that? So you take A times D, and then you subtract B times C. And we want to make sure that it is not 0. If it's not 0, then we say it's invertible. And we find the inverse using this formula right here, okay? So let's go ahead and do that for A. So let's find the determinant first. Another notation that you might see for determinant is just straight bars, like that. So 3 times 6 is 18, minus 2 or 4 times 5 is 20. I was already subtracting in my head. Negative 2, which is not 0. Okay, so therefore, the inverse is 1 over negative 2 times, we're going to switch D and A, and then we're going to take the negative of B and C. And you can leave it like this, or we can go ahead and multiply on the inside, so negative 3, 2, 5 halves, negative 3 halves. And that's going to be my inverse of A. Now, one thing that is going to be true is if I multiply A by its inverse, I get the identity matrix. And I know we talked about in the video before, you can't then switch with the commutative property, but it is also true that A inverse times A also gets you the identity matrix. Okay, we'll do a little bit of that here in a minute. All right, if A is invertible, n by n, so a square matrix, then for each B in Rn, we can take A, x equals B to be actually the inverse of A times B. The reason that that works is, again, if you take A inverse times AX and apply that to both, A inverse times A, essentially they cancel out, they get you the identity matrix, and so that's why this ends up working. So this is the matrix, if you notice, the coefficient matrix of A, so we already found A inverse in that first problem. Okay, and it wants me to then solve that here. Now, we would have done this before by doing an augmented matrix like this, doing row reduction. So this is just another way in order to solve this for x. So x must be A inverse times B. So that gives me negative 9 plus 14, and then 15 halves plus negative 21 halves. And so I get 5, and then negative 6 halves, so negative 3. And again, you could do reduce methods on this matrix, and you're going to end up getting the same thing, 5, negative 3, when you solve that. All right, so we already talked about theorem 6 a little bit. If you have an invertible matrix, then if you take the inverse of the inverse, you get back to the original function. Okay, just like how the transpose worked, AB inverse is B inverse times A inverse. So very similar to that transpose. And it is true that A transpose inverse is the same thing as taking the inverse and then the transpose, and that is fine. So these are all properties and theorems of the inverse rules for our matrices here.